Okay, let's pick up where we left off. So remember last time you guys were all trying to get me to delete things on my machine by playing with hard links. So remember we started talking about file systems, and we're largely talking about how we store and use metadata in file systems. Remember, so we were talking about things like naming and how we lay out directories on disk. Now, before we start talking about how we actually lay out the data of files on a disk, one thing we didn't get to last time, which I wanted to talk a little bit about, is protection. If my computer will cooperate. Oh. Or it'll just crash. Okay. Okay. So one of the functions of our file systems is also to control sharing among our files, right? Because certain files you might like to access, you don't want other people to be able to access. Other files you might have, you do want other people to access, right? So the OS is providing that to us as well. So there's essentially two different approaches used to controlling access to files. One of them is what we call access control lists, ACLs. That's a Windows term, so this is the approach that Windows uses, which is pretty straightforward. For each file, you're going to keep a list of users that can actually access the file, as well as what type of access they have, right? Because there's various types of accesses. You might have access to read a file, but not to change a file, or you might be able to execute a file. So various types of accesses. Now obviously the problem with that is that you could have sort of a very long, complicated list, and you're basically having to control these lists for every single file, right? So you're potentially storing a lot of extra information for every file. So the second approach, which is used in Unix, is basically rather than keeping a complete list of all of the users that are able to access a file and all of the specific permissions that each of those users has, we're just going to use a few bits, right? So this is called using access control bits. So the Unix approach is basically we're not going to specify permissions for every single user individually. We're basically just going to have three categories. We're going to have the user itself that owns the file, and then the user is part of a group, which is multiple users. And then there's everyone apart from the group, right? So those are basically the three categories. There's the user itself, and then there's the user's group, which is includes the user and is a superset of that. And then there is everyone, all users on the system. And basically we're going to store whether the user, the group, or everyone can either read, write, or execute the file, right? Those are the three basic types of accesses. So essentially the way we do this is just using 9 bits, where each bit is basically going to say, so the first 3 bits are basically going to say, can the user themselves read, write, or execute the file? Then 3 bits for the group, and then 3 bits for everyone. So let's actually look at a quick demo of that. I'm sure some of you are familiar with this, but if I create some file, so right here, this is basically showing the 9 bits that I just mentioned, right? So this file is owned by me, S. Barker. I created that. So these first 3 bits basically say what I'm allowed to do with the file. So right now, I'm allowed to either read or write the file. The 3rd bit is execute it. I'm not allowed to do that. So if I try to execute the file, it's going to say permission denied. Right, because even though I created the file, I can read or write that, I actually don't have execute permissions on that. And then, everyone else, the group, which, I'm part of this group wheel, but there are lots of different groups on your machine for various things. The group and everyone outside the group is allowed to read this file, but not write it. Right, and you use the, chmod command to actually basically manipulate these bits. Right, so if I say something like group plus write. So now essentially all I've just done is flipped that one bit, saying that now my group is allowed to actually write this file, right? And so then if I wanted to give myself execute permissions, I can just do that, and now it will actually let me execute the file. Now obviously it's an empty file. Executing it doesn't do anything, but essentially, big upside here is obviously that rather than having to maintain potentially a very long list of information for each file, we can encode all this information in just 9 bits. Right? And you can actually also use chmod in terms of those bit settings. Right? So for example, let's say I wanted to give everyone all permissions to this file. I can say chmod 777, and that sets everything. And right, the reason for that is, what's the binary value of 7? 111. Right, so all I'm essentially saying here is set these 9 bits in groups of 3 to 777, which is all ones. Make sense? Right, so benefits of access lists are it's sort of the most flexible approach where you can sort of give any set any configuration of permissions you want, but benefits of access control bits are we're doing this with very, very little information, and in almost all cases that's still going to be flexible enough for what you typically want to do in terms of sharing. Questions on this before we move on? Okay. So that's pretty much it for talking about metadata. So now the main topic for today is we're going to start talking about how we actually implement our file systems. So first we're going to talk a little bit about how disks actually work, how hard disks actually work. And then we'll talk about how we actually are going to lay out data on disk, right? Because that's one of the main functions that we haven't talked about at all is, of course, our files have data that is actually stored on the disk. How do we actually do that? So first let's talk a little bit about how hard disks work. So essentially you can think of a hard disk as you have some magnetic surface that stores data. And basically a disk surface is made up of a number of concentric circles. So those circles are basically called tracks. Right? So here's some surface of the disk, and there's a bunch of circles, and those are each called tracks. And so the tracks basically subdivide the surface of the disk. And then within each track, that's further subdivided into pieces called sectors. Right, so each one of these tracks is broken up into a number of sectors. And the sector is basically the smallest unit of I/O on the disk. So the size of a sector on a typical disk is usually 512 bytes. So basically when you tell your disk to either read or write data, it's always doing it at the level of sectors. Right, so even if you just want to read or write 1 byte, your disk is actually reading or writing an entire sector, which is 512 bytes. So while your disk is running, the whole surface, the disk is spinning, and you basically have a disk head that is actually reading the disk while it spins underneath it. Right. So this is basically the disk head that's going to be positioned over one of these tracks. Right, because the disk is spinning, all of those tracks are spinning. And in order to actually read a specific piece of data, which is a specific sector, the disk head is basically going to position itself over one of these tracks, one of these tracks. So the disk is spinning, disk head is positioned over one of the tracks, and once you're over the right track that you want, you basically just wait until the sector you're looking for spins under the disk head. Right, so if I'm looking for this sector right here, then the disk head's going to position itself over this track. The disk is spinning, and sooner or later, that sector is going to be under the disk head. And that's where we're actually reading or writing that data as the disk spins. So, to get to a specific sector, you move the disk head, and then you wait for the disk to spin to actually get under the disk head. So the way we kind of described it is almost like how you think of a CD, right? Because a CD is just sort of one surface that spins. But the way a typical disk actually works is you basically have a bunch of these surfaces stacked one on top of another. right? And so these are basically, we call these platters or surfaces, right? So in this picture we looked at previously, it's sort of just looking at one surface, but in an actual disk, you'll have maybe 8 surfaces all stacked on top of each other. And basically, the benefit there is you're storing data on both sides of the surfaces, and you basically have this, ARM assembly, which is sort of a bunch of disk heads, reading each of the disk surfaces, and they're all spinning as one unit. Yes. Multi-layer disks. I don't actually know exactly how. I mean, my guess is that it's just much, much higher density, but I don't know specifically. Like, I mean, if your question is like, how does a CD differ from a Blu-ray? I mean, my guess is obviously it's much higher density. More specifically than that, I'm not really sure. Yes? Oh, okay. Yeah, yeah. Yeah, I mean, there may be mechanical differences that I'm not familiar with. Yes? Yes. So basically, you have a bunch of this. This whole thing is basically called the ARM assembly. That's usually the term. And there's basically a read and write head on the top and bottom of this. This top one would be reading the underside of the top platter. Then this one is reading the top side of the second to top platter. Yes.
Can you do the reading in parallel, or kind of only read?
No. Yeah. This seems like it would be a great thing if we could just sort of read from everything all at once. But no, you basically are only reading from one read-write head at a time. And remember, one thing to keep in mind about why reading things in parallel might not actually be super useful is that this whole assembly is basically moving as one unit, right? So the entire disk is spinning, and so you can't sort of independently control what parts of the disk each of the read-write heads are actually reading. You're, specifically at one track. So actually another term. The term cylinder basically refers to this case, the thing that there's a corresponding track on every platter, right? Because if you have a bunch of concentric circles on each surface and you have a bunch of surfaces stacked, a cylinder basically refers to the set of corresponding tracks on every single platter. So at any given time, your disk is spinning and your read-write heads are positioned over that one specific cylinder. Right, so potentially, you could envision being able to read in parallel from the same cylinder, but that might actually not, that might not actually be super useful. Yes?
Are all arms at the same position, at the same track?
Yes. Yeah. Yeah, everything is basically moving as one unit as the disk spins. Yeah. So this is just essentially a nice way to, stack a lot more information into the same disk. I think there's another question. Do you have a question? What's that? Okay. So now one thing here is obviously this is how a conventional hard drive works, right? If you have something like a solid state drive, like most laptops, for example, today come with a solid state drive, that's completely different from this picture, right? This is a hard drive that has a magnetic surface that's actually rotating. A solid state drive has basically no moving parts. I mean, when you think about how a solid-state drive is being accessed, it's actually much more like main memory than something like this, where you're basically just directly accessing any part of it. So we're essentially just going to be talking about hard disks and some of the considerations, especially with regards to how performance looks on a solid-state drive versus a hard drive. The considerations are going to potentially be very different. But for the moment, we're just going to assume a standard magnetic spinning hard drive. So let's consider, in this picture, what are sort of the sources of overhead, right? Because we've talked a lot about how disk, reading and writing to disk is really, really slow. So what are sort of the components? If I, want to read this, if I want to read this sector over here, what's determining basically how long that's going to take? Yes. Right. So one thing is that the disk head is somewhere over here. The disk is spinning. If we want to read this sector over here, we have to wait until it actually spins and gets under the read head. Yeah, so that's one source. What's another source? Yes?
How quickly the head can actually read it from the surface?
Yeah, so that's another one. Now, how quickly we can actually read it. Right, so that would basically be the bandwidth of the disk. how quickly your disk can actually read data. Yes. Right. Yeah. Another important one is right. We have to actually position this arm over the right track. Right? Because if we want some specific sector, it's some sector of some specific track or cylinder. Right? So we have to position the read head over that track and then wait for the disk to actually spin under that. Right? So those are essentially the main sources of mechanical delay when you're actually doing a disk read or disk write. Now, obviously, there's also going to be a little bit of overhead for the CPU to actually start a disk operation. Right, you're actually issuing something to the device driver and actually doing that in software. But really, the main sources of overhead are positioning time, which is basically two components. We have what's called the seek time, so that's where we're positioning the head over the correct cylinder. And then once we're positioned over the correct cylinder, we have the rotational time, which is waiting for the disk to spin so that we are over the right sector. Right, and then there's actually the transfer rate, which is, once you're actually transferring, how quickly can you do that? Now, transfer rate on a typical hard disk is usually, maybe 100 megabytes a second, for example, something in that ballpark. Which, if you think about how your machine, is usually operating, very rarely are you actually trying to read that high a speed. So really, the transfer rate is not the bottleneck here. The bottleneck here is this positioning time. Right, because that's on the order of maybe 5 to 10 milliseconds, right? Because those are mechanical delays, and you're doing those a lot, right? So essentially, the reason I/O is so slow is mostly due to the positioning time of having to move the arm and wait for the rotating disk. And then, of course, the CPU overhead is a tiny, tiny fraction of that, so we don't really need to worry about that when considering, the performance of the disk. So, again, and just to mention solid-state drives one more time, what's essentially the big difference here with solid-state drive performance? Yeah. Right. Essentially, positioning time is gone. There are no moving parts in a solid-state drive, so you don't have to worry about that at all. So typically, your bottleneck is simply, transfer speed. Now, there are some other considerations with solid-state drives, such as the fact that if you write too many times to a solid-state disk, you can actually wear out the disk. It can only essentially overwrite the same piece of data so many times. So some other issues that you run into with solid-state drives, but we won't really be talking about those. So now let's start talking about how we actually lay out data on disk. So for each file that we have data stored for, it's basically organized as a bunch of blocks, right? So essentially, we can largely think of as a block as roughly equal to a sector. Now, basically, the term block is basically referring to a file system construct, right? So a file is composed of a bunch of blocks. And basically, from the OS's perspective, the disk is essentially laid out as a big array of blocks. But actually, at a hardware level, right, we have sectors. And so you can essentially assume that a block is equal to a sector. Now, in practice, a block is typically a multiple of a sector. So a block might be 2 or 4 sectors, 1 to 4 kilobytes on average. But essentially, we can just assume that a block is roughly equal to a sector. So we basically need to take file blocks and decide where they are in the disk, which is basically going to mean what platter, what cylinder, and what sector. Now, a sort of simplified version of how we can actually just consider numbering sectors is, let's just say we have 2 tracks. Let's just say we have 2 tracks and 4 sectors in each track. We can essentially just start numbering from 0. Say the outermost track will have, sector 0, sector 1, 2, 3. And then once we've completed one cylinder, move to the next one and say, 4, 5, 6, 7, so on and so forth. So you can essentially assume that given the block number, we can very easily translate it to, a track number and a sector number within that track. So the big performance issues here are, what are we? So we need to be able to support both sequential and random access. So remember from last class we talked about those as essentially the 2 main access patterns. right? Sequential access is where you are starting to read the file and you're basically just reading it straight through, right? That's sequential I/O. And then random or direct I/O is where you're potentially jumping around either within a file or between multiple files. So we want to be able to do that efficiently, and so then we need to consider, how to store all this information as well as how to actually lay out the files on the disk. So, for every file on the disk, we're obviously, keeping some metadata with that. We've already talked about that. So, we can just call this the file descriptor. Sometimes that's actually, I think the book calls that a file control block as well. So there are a few different terms, but essentially that's just the piece of metadata that we're maintaining, describing the file, including both its attributes as well as where it's actually laid out on the disk. And a few important properties that are generally true of just about all disks and all systems are very important to keep in mind. So one is that most files on a typical system are very small, right? So you have a ton of files on a typical system. Most of them are actually on the order of maybe a few kilobytes, right? So lots of files, most of them are very small, but actually most of the space on your disk is not taken up by those large number of very small files, but a small number of very large files, right? So if you have, say, a movie on your computer, that single movie file may be a couple of gigabytes in size, right? So it doesn't take too many of those very large files to actually take up most of the space on your disk. So, we obviously want to be efficient both at dealing with small files and large files, but essentially keeping track of small files is almost more important because that's the common case, because almost all files on our systems are going to be very, very small. Right, so we want to be able to access, the per file cost should be very low, but obviously we also want to be able to read, large files. So let's consider how we can actually, store these files on disk. So, this is hopefully going to sound a little bit familiar from our discussions of memory management. Let's start with sort of the simplest possible way is, contiguous allocation, where, when we have a file and we need to lay it out somewhere on disk, we have a bunch of free blocks of the disk, right? Because remember, from the OS's perspective, the disk is basically a big, huge array of blocks. So we're just going to pick some, contiguous chunk of free blocks and lay out the file there, right? And so then, in the file descriptor, things are very, very simple. The only thing we need to do to know where the file is on disk is, the start location and, the number of the size of the file in terms of blocks. Right, so, if we have this disk here with 8 blocks, I can just say, my file is going to start at, block 3, and it's going to be 3 blocks long. So, obviously then it's 3, 4, and 5, and that's just going to describe, where the file is. Right, so really simple. That's obviously nice. Now let's consider how well this actually does for our two types of access patterns. Right, so we have sequential access and we have random access. So how is this approach going to do if we're doing, sequential access? How efficient is this going to be? So if you have some big file and you just want to read it sequentially, yeah. Right, so it's going to be the most efficient, actually, approach. This is the best possible thing you can do for sequential access, because all you're essentially doing is just, reading the file as the disk is spinning. You're never having to actually reposition the disk, right? So essentially, it's basically one disk seek in order to do this. So you, of course, when you're reading it, you have to, do the seek and the positioning delay to get to the start of the file, but that's essentially it. Then you can just read it sequentially. Question?
I was just wondering if the disk stops spinning between speeds.
No, the disk basically spins at a continuous speed, right? Because when you buy a disk and it basically says what the rotational speed is. So like a typical disk is usually 7,200 RPMs. Now you can get disks that spin either faster or slower. Like a really fast hard disk is usually, I think they go up to about 15,000 RPMs. A really slow disk you might get in, not so much nowadays, but a couple of years ago, oftentimes the disk in a laptop would spin at maybe 5,400 RPMs. So that, of course, means the positioning time is longer since the disk is spinning slower. But yeah, the disk is, while it's on, is spinning at a continuous rate. Well, I should say that you can have your computer can put your disk to sleep, right? And so you can put the disk to sleep and essentially stop spinning it. But then when you actually want to use it, you have to wait for the disk to spin up again. Any other questions? Okay, yeah. So we said that this is great for sequential access. How about for random access? So if I want to read read a bunch of random files, I mean, what is the disk going to have to potentially do? Yeah.
It's going to have to not only wait for the disk to come around, but it might have to change which channel it's on.
Yeah. So you're going to have to wait for the disk to get to whatever block of the disk that you want. But how about if you want to do something like, let's consider random access within a specific file, right? So let's say that remember what we're storing here. We're basically storing a file as just the start position, the start block. Say block 2, and it's 4 blocks long, for example. And let's say I want to directly access the third block of the file. Yes. Right, exactly. It's still going to be easy because if you want to access the third block of the file, all you're basically doing is an offset from the start position, right? Because if you know that your file starts at block 2, and you want the third block of the file, then, right, it's just going to be block 4 is going to be the third block of the file because you're just basically doing an addition, right? So it's still just going to be the one positioning time to look for any part of the file, right? And that's basically what random access is, where we're, potentially looking at any part of the file. So that's still going to be efficient. So this is actually good both for sequential access and random access. Now, obviously, as was mentioned, random access is still always going to be slower because you're waiting potentially for the disk more times, but this scheme is still efficient for that. So, what's sort of the problem with contiguous allocation if it's good for both sequential access and random access? So what's the downside of this approach? Yes.
What happens if you want to rewrite something?
Right. So this is essentially the same problem we have with memory allocation, where if you have a bunch of blocks allocated to some file, and you have maybe a bunch of blocks laid out one after another, a bunch of files laid out one after another on the disk, then if one of the files wants to grow, you potentially don't have any extra blocks right there, and so you're going to have to pick up the entire file and copy it somewhere else on the disk, which is going to be really expensive. Yeah, question? Yeah, so you could be potentially wasting bits of a sector. Right, that's essentially where we're just sort of taking that as a given, saying that the sector is the basic unit of I/O, but that's true. Yeah. Well, this is all sitting on the disk, so right, that's sort of at a higher level of just what the OS is assigning to, a specific file. So, I don't think sharing doesn't really have a lot to do with how it's actually laid out on the disk. But basically, the main issues are changing the file size is potentially a problem because you have to move the entire file, and that's going to create the same problem we had with contiguous allocation in memory of we're going to end up with potentially a lot of fragmentation. So this approach was actually used in early personal computers where we just sort of laid out everything. Obviously, it's sort of the easiest possible thing to do. Now, there's basically still one case today where we actually do use this approach. Anyone have any ideas? When might contiguous allocation still actually make sense? Yeah. Long-term storage on tape. That's true, and why is that true? Right. Once you write to that, you're probably not going to be changing it, right? And this is essentially any kind of a write once disk. So what's another example of a write once disk I'm sure you've all used? Yeah. Right. A CD or a DVD. Right. When you burn a CD, you're writing data to it, and then it's never changed again. Right. So contiguous allocation still makes sense there because your file sizes are never changing. You're never going to have fragmentation because you're never deleting files. Right. If you're just laying everything out up front, contiguous allocation makes a lot of sense. So we actually still use that when you're doing something like burning a CD or a DVD. So, but obviously when we do have, changing files, not the best approach for these reasons. So, let's consider another approach, which is using linked files. So the idea here is we're basically going to keep a linked list of where subsequent blocks of the file are located, and that's going to actually let us, lay data anywhere across the disk. We're not going to enforce that it's, contiguous. So basically now what we're going to have is in the file descriptor, we're going to have a pointer to some block of the disk. And that's going to be the first block where the file starts. And then in each sector that's storing the actual data of the file, we're going to have another pointer to the sector that follows it. All right, so if we have this file descriptor here, and we have some pointer that's basically saying, which platter, cylinder, and sector our file starts at, our data starts at, and then we could do something like, say, allocate 3, say, this just as an example, we could say allocate 3 bytes at the end of every sector to say where the next sector starts. Right, so we have a pointer here, and then at the end of this sector, we have another pointer that points to another sector, and these sectors could actually be scattered, all over the place. Right, so we basically just kind of have, pointers pointing to various parts of the disk that actually is going to lay out the file. And then we can also, in order to keep track of empty blocks, right, because now when you actually want to look for an empty bunch of blocks, you can't just look for, a contiguous set of blocks. We can actually just keep another linked list with all of the empty blocks of the disk. Right, so if there are, blocks 2, 7, and 9 you're not using, you basically just keep a linked list of those saying that this is the linked list of free blocks. So then when you want to, allocate a block, you just take it from the linked list of free blocks. So let's consider how this works. So are we going to have fragmentation in this approach? No, right? No fragmentation here because we can lay out anything we want, right? Any sector can point to any other sector as the next block in the file, right? So no fragmentation here, so that's good, right? So file size changes. So how difficult is that if you, change the size of your file? Yeah. Right, so very easy because you're basically just manipulating that linked list of free blocks. And your file is represented as a linked list. It's obviously very easy to add a block onto the end of your file. You could even stick blocks into the middle of your file, right? Because you could take, if you want to, if you have a big, huge text document and you're modifying some data in the middle of the document, you could potentially just insert a new block of data without actually doing anything to the blocks that precede or come after, right? So that's very flexible. Now, let's consider, again, the two types of access, sequential and random access. So how is this going to do for sequential access? If you have a big, long file and you want to read the whole thing sequentially, how is this going to do? Yeah. Excellently. So it may be easy to see how to, right, because you're traversing the list, but what is traversing the linked list actually doing on the disk? Right, yeah, where are you going?
Yeah, and potentially, like, you'd have to read one block, have the CPU look at where the next block is, set the big request for that block.
Right, exactly. Like, if we look back at this, we read some sector to start with, and then at the end of that sector, it could potentially point to some completely different sector, somewhere else on the disk. So then we're going to get another positioning delay while we actually, potentially move the read-write head and wait for the disk to rotate, read that sector, and then do it again and again and again. Right? So previously, with contiguous access, we only have to position the disk once. Now we're potentially having to position the disk for, every single sector. Right? So there's basically one seek and one rotational delay for every single sector. So we've gone from one seek and one rotation to n seeks and n rotations, right? So that's pretty bad. And how about random access, right? So if I have some big long file and I want to read, the middle block. I want to read something in the middle. How efficient is that going to be? Yeah.
Go up to number 2C. There's no sort of pointer to the middle. You have to from the beginning.
Right. Right. So random access is also going to be inefficient because if I want to read, if I have, five, or I guess here we have four sectors of data, and I want to read the fourth sector, I basically am going to have to traverse the entire list to actually get to the end. Right, so even if I only want to read one sector, if it's somewhere, at the end of the file or in the middle of the file, you still are going to have to do the same process of traversing the list, incurring a bunch of seat delays and rotational delays. So, obviously the exact cost of that will depend on where in the file you're trying to get to, but random access is also going to be pretty inefficient for that reason. So this actually type of approach is actually used in some file systems. This was used in DOS and most FAT type file systems. There's a bunch of variants, but essentially they're all using something like this, where files are linked together like this. And as I mentioned last class, I think this type of file system is actually still used on things like flash drives. Not really any hard drives nowadays, but still small devices use this kind of thing. So, this is obviously not good from an efficiency perspective in terms of actually reading and writing things. So, let's consider a different approach, which is rather than keeping a linked list where you're just pointing to the first block of the file, now let's actually keep an index where in the file descriptor we're going to keep pointers to every single block of the file. Right? So in the linked list case, you just have the one pointer to the starting block. Now we're going to keep a bunch of pointers to every single block of the file. Now, those sectors could still be scattered all over the disk, right? So we're still not imposing that they're actually allocated, laid out continuously, but we're going to be able to look them up, immediately, because we can just, if we want to look at the, last block of the file, we just go to the last entry in the index and just look up, that file. So what's this going to mean for the size of the file descriptor? So how much information are we now storing in the file descriptor? Right, because in the linked list case, in the linked file case, we're just basically storing one pointer that goes to the start of the file, and that's all that we're needing to maintain in the file descriptor. So now what are we needing to maintain? Yeah. Right. So now you're essentially having to store a pointer for every single, for every single block, every single sector of the file. Right. So potentially, very large. And more to the point, you actually have to, right? You are actually allocating these structures up front, because whenever you create a new file, your OS is basically allocating one of these, file descriptor data structures. And so you're basically having to allocate an entry for every single possible block of the file, even if your file is still very small. Right? So the OS, of course, doesn't actually know the size of the file that it may ultimately be, right? You could initially create an empty file and then write to it, and ultimately it might become a very large file. But the OS doesn't know that in advance, so you're basically having to actually allocate this entire structure up front. And so, what's that going to mean if you have potentially, very large maximum file size? Yeah.
You have a very large overhead for the array size.
Right. So basically, the larger you want your files to be able to grow to, the more you're going to basically waste allocating these large data structures to actually store the files. And that should hopefully strike you as a bad idea based on the property we said of file systems earlier, which was what? What did we say about most files in a file system? Yeah. Right. Remember we said that the vast majority of files in a typical system are very, very small. So we would like to, of course, be able to support very large files, but we don't want to have to pay a big price on every single file, even really small ones, in order to be able to support those large files. So, one other thing I should note here is that even though we're allocating all of these pointers, we're of course not actually allocating the blocks on the disk. Right? We're basically providing entries here to point to every single block of the file, but the actual blocks on the disk themselves are only allocated on demand, right? So as you're growing your file, you're actually allocating the space on the disk, but it's not like, you create an empty file and all of a sudden, 2 gigabytes of your disk are taken up by that. So let's consider how this does for performance. So obviously the issue of the size of the file descriptor is not great, but let's consider how efficient this is going to be, right? So with sequential access, how is this going to do? Yeah. Right. Basically, going to be the same thing as the linked approach, right? It's still not going to be as good as the contiguous allocation, right? Because we're walking through all of these blocks, and the blocks are actually located, remember, they could be distributed all over the disk. So we're still potentially having to do a lot of disk seeks, but essentially going to be the same as the linked file case. Now, how about random access? Yeah.
Wouldn't it have to be more because you have to go back to the file description, which would be
So
would be on this?
yeah, so these data structures are actually stored on disk as well, right? Because all of this stuff is supposed to be persistent, right? If your computer crashes, even if your data is all still sitting on the disk, if you have no idea how it's laid out, it's essentially useless, right? So all of these things are actually stored on the disk as well. Now, typically, right, you're not going to do another read every single time to access one of these pointers. You'll read a copy of the file descriptor into memory and use that. But this is ultimately sitting on disk. You'll read it into memory when you actually want to use it, of course. Yeah, basically all of these approaches, when you actually want to read a file, you still have to basically read the file descriptor, which is ultimately sitting on the disk. I mean, ultimately you'll have a copy of it in memory once you're using it, but initially it's going to be sitting somewhere on the disk. Yeah. Right. So we said this was the same as a linked file for sequential access. How about random access? Right, because we said that the linked file was really bad for random access because you have to traverse the entire list potentially. So how is this going to do? Yeah. Right, so this is basically solving that problem we have with the linked file, where now we have the whole index laid out in the file descriptor. So if we want to read the last block of the file, we just go to the last entry of the index, and that tells us exactly on the disk where to go. Yeah.
Yeah. So like, let's say you have a 4 terabyte hard drive, don't you have to, assuming that like you can allocate 40 gigabytes, like 4 terabytes, that every single file descriptor would have entries with 4 terabytes?
Yeah, so the question was, if you have a huge disk, aren't you going to have to allocate a ton of entries to be able to store potentially a file up to 4 terabytes? So actually the answer to that is basically that the file system you're using is going to actually impose a maximum file size. And the maximum file size is not directly related to the size of your disk, right? So that's actually one of the major problems with simple file types that we may have used 10 or 15 years ago that are not really in use today, is that their maximum file sizes were quite small. So I think, for example, most typical FAT type file systems have a maximum file size of, I think, 2 gigabytes is typical. So yeah, so if you basically, the way we laid this out here, we can basically specify what the maximum length of the file is. And we can essentially decide what that is. We could decide that we only want to allow pretty small files, and then we won't have to keep very much information in the file descriptor. Or we could say, I want to allow massive files, which is nice for flexibility, but means then we're having to store a ton of data. Yeah, so that's basically the trade-off here is between providing a large enough maximum file size and storing all this data in the index. Yeah. But that's essentially the main problem with this approach that we'll actually address in the next approach. Other questions on this? Right, so advantages here, we're not wasting very much file for files themselves, right? Because we still are not having the fragmentation issue because we can still lay things out however we want on the disk. We are wasting space in the file descriptors themselves, since most files are going to be much smaller than the maximum file size. Sequential and random accesses are both, easy, not as efficient as the contiguous case for sequential access, because remember we said that the contiguous allocation case is basically optimal for sequential accesses. But this is still reasonable. But disadvantages, as I said, we're having to decide what the maximum file size is, and we're still doing lots of seeks because the data is not contiguous. The same as we had in the linked file case. So basically we want to address this issue of these dealing with a large file size without huge file descriptors. So in order to deal with that, we're going to use this idea of a multi-level index file. So this is actually the type of file allocation used in just about all Unix-type file systems. So this is actually a nice example where we're not sort of using some nice simplified picture of how things actually work. This is basically how things actually work. So essentially the idea is that your file descriptor is going to have some small number of pointers. So let's just say, for example, the exact number is sort of arbitrary. But let's say that we have 14 block pointers in the main file descriptor. So basically, most of those are basically just going to point to pieces of data. Right? That's the same as we had in the index case, where in the file descriptor you have pointers that are pointing to pieces of data, pointing to blocks on the disk. But then at the end of the file descriptor, you're going to have another pointer that's not pointing to a block of data on the disk, but actually pointing to another index. Right? And so that another index is going to be a set of pointers, and those pointers are pointing to actual blocks on the disk. Right? So in this example, we have maybe 14 block pointers in the file descriptor. 12 of them are pointing to blocks on the disk. The 13th one is pointing to another index file, which has maybe 1,024 more pointers. Each one of those pointers is pointing to the disk. Right? So that's basically one level of indirection. You have a pointer to an index with another pointer to the data. And then you could have multiple levels of indirection as well. Right? So in this example, we could have a 14th pointer points to another index. But this index is pointing to other indexes as well. Right? So this index could point to 1,024 pointers. And each one of those 1,024 pointers points to another index of 1,024 pointers. And those pointers finally point to pieces of data on the disk. Right, so this is basically multiple levels of indirection. Is there a question? Yeah.
So intuitively, you want files to be accessed more frequently higher up on this hierarchy.
Right. So essentially, the way we're laying this out is, as the file grows, we're starting here, laying out this data, and as the file needs more data, then we're going to go to this index file and start laying out these blocks. And once we've exhausted that, then we'll go to the second level of indirection and start laying out data there. Does that answer your question? Another question?
Yeah, just why wouldn't you just have all other than the last bit pointing to another index file, and then in the next index file, you're going to have space just pointing to another, instead of having the last.
Wait, you're saying why wouldn't you have?
So right now you say, okay, the first 12 point to data, and then
Right.
and then the second to last is going to point to an index file, which is pointing to data.
Right.
The last one pointing to an index file, which is pointing to data. But why don't you just have your last one point to an index file, if you're out of space there, and have the last point in that index file?
So you're saying, why don't we just lay out data here, and if we run out of space, have the last one point to an index file, lay out data there, and if we run out of space, have the last one point to an index file?
Yeah, so why don't we just do that instead of having two?
Yeah, so we could do that. What would be the downside? Anyone think of a possible downside with doing that? What's going to happen as your file gets larger and larger with that approach? Yeah.
You have to go through
Right. The issue there is essentially that as you make your file longer and longer, you're potentially adding basically an unlimited, potentially number of redirections. Right? Because if you run out of space here, you redirect to another index. Run out of space here, redirect to another index. And if your file is huge, you may end up with lots of levels of indirection. And so if you want to access data at the end of the file, you're still going to have to do what we, more or less what we did with the linked file, which is traverse a whole bunch of pointers looking for the piece of the file you want. Yes? Yes. So the reason this saves space is basically you're only allocating these index files when you actually need them. Right? So if you have a file that has only, 6 blocks of data, you're basically not allocating any of these additional index files. You just have the 6 blocks that are pointed to from the file descriptor itself. Yes? The reasoning of 14 is that's what the designers of Unix decided to use. Some file system designer decided that 14 was a reasonable number. Now you could think of why that, probably the choice of 14 was due to some type of experiment looking at the typical size of files, right? Because if your system say, if say 90% of the files, just, I'm sure this is not true, but if, 90% of your files are 14 blocks or less, or 12 blocks or less, or whatnot, maybe that's a reasonable choice. Yeah, 14 is basically the value actually used in Unix. This right here, this picture, is basically the picture used in Linux. So the actual choice of numbers are arbitrary to the multi-level index approach, but this is basically what your system is doing.
So it's like
Upgrade in what sense? Yes, actually. So right here we have 2 levels of indirection. A modern file system actually often has 3 levels of indirection, right? So they would add a 15th pointer, and that 15th pointer points to an index file, and each of those indices point to another index file, and each of those indices, you get the picture. It's essentially yet another level of indirection with more index files. Yes?
So I'm looking at the next file size, and it seems like it's just arbitrary. Like NTFS is 16 exabytes.
Yeah, I mean, right, so the benefit here is that, we're allowing potentially very, very large file sizes, right? Because these levels of indirection, well, actually, that's a good question. Let's consider that. So supposing we have this approach right here. What is the maximum number of blocks in a file? Yeah. Oh, okay. Yeah. Well, supposing that this is the actual layout we're using with 14 pointers and 2 levels of indirection with 1,024 pointers.
So 12 plus 1024 plus 1024.
Right. So basically very close to 1024 squared, because we can store 12 blocks of data in the file descriptor, and then 1,024 blocks of data using the first level of indirection, and then 1,024 squared, right? Because each one of these entries can store another 1,024 blocks, right? So basically 1,024 squared is the maximum file size here. Now, if we were to add a third level of indirection, then what would the maximum file size be then? Right, 1,024 cubed. Right, because then each time you're adding another level of indirection, you're just multiplying it by another 1,024. Right, so after a certain point, with 3 levels of indirection, which is, as I said, what most typical file systems are using, you're basically getting to the scale where you actually can have a single file that takes up your entire disk. And once you're at that level, there's essentially no reason to continue making things larger. Now, obviously, disks are continuing to get larger, so maybe in the future you'd add a 4th level of indirection, but after a certain point, right, this is basically exponential growth. So the file sizes you can support, get very massive very quickly. Yes. Do SSDs use this? Well, basically, the file system that you choose, you can apply to whatever disk you want, right? Because a disk is basically just a bunch of blocks or sectors laid out. And when you actually format your disk as a specific type of a file system, you're basically laying out the data structures to manage it this way. But the disk itself, all it's basically seeing is read this sector of the disk, write this sector of the disk, so on and so forth. And all of this stuff is actually managed in the OS. Right, so let's just recap what we're sort of getting for doing this, right? Because the problem in the indexed approach was that we had these really, really huge file descriptors potentially in order to support large files. With this approach, we have very modest size file descriptors, but we can still support large files by using these extra levels of indirection. And by just adding a few extra pointers, we can basically make our files as large as we want. Now, we are making sort of a trade-off here, which is what's the performance of small files versus larger files in this approach? Is it the same or different? Yeah. Right. We're basically explicitly preferring small files here. Because if your file is really small and fits all in the file descriptor, it's the same as the regular index case where you can directly index each block of the file. But if your file is really, really large and you have blocks sitting down here in the second level of indirection, in order to access any of those files, you are still having to traverse some of the index files to get there. Right, so we are basically making it a little bit more expensive to access very large files, but it's still going to be reasonable because there's going to be at most maybe 2 or 3 pointers we have to follow in order to get any block of the disk. Right, because in the extreme case, in sort of the linked list, the linked file case, you potentially have to traverse the entire file one at a time, one block at a time. Here we still do a little bit of traversal, but it's only going to be a few pointers at most. So this is still going to be reasonable. So actually, just a little bit of Unix terminology. The file descriptor data structure here in Linux is basically called an inode, which may be a term some of you have heard of. But basically, if we remember from last class, when we were running those commands and we were saying ls-i, and we were getting those numbers, remember we were comparing those numeric numbers, which I basically said were sort of the internal file identifiers. Those are basically the inode numbers in Unix. So that's actually what the I stands for. It's basically just giving you, the ID of this data structure here that contains, all the usual metadata we expect in addition to the pointers to, the first couple of blocks and then the indirect pointers to the next index files. So one thing I actually also want to mention is that, remember I said that, these file descriptor objects also have to be actually stored on disk. So the way this is typically done is your file system is basically organized into blocks and what are called super blocks. And super blocks are basically components of your hard drive that are laid out for storing things like file descriptor objects. So when you actually go and take your hard disk and you say you reformat it, right, you run some utility to reformat it, and that's when you specify, the type of the file system and so forth. It basically is allocating some chunk of your disk and basically allocating a bunch of space for these file descriptor inode objects on the disk. And then you basically have a bunch of unallocated free inodes. And when you actually are creating a file, you're basically saying, give me one of these free inode data structures, and then I'll start using that for my file. Right, so those are essentially what those inode numbers are. It's basically saying, give me the 100th inode data structure on my disk, and I'll use that for my file. Any other questions on multi-level indexes? Okay. Right. So advantages here. Obviously, we're supporting incremental file growth, right? And we can do that only allocating those index files as we actually need them. So a small file is going to be very nice and compact. We can support a large file with only a little bit of a performance penalty. We already said, this approach is optimized for small files. And there's actually a further optimization that's actually used in Linux, which is suppose we have something like this, but suppose you have a file that is, say, a couple of bytes, and that's it. Because you could have potentially really, really tiny files. What might you be able to do to optimize a file that's only a few bytes? Yeah. Yeah, exactly. you can take that data and just actually directly stick it in the file descriptor. Right? If you have only a few bytes in your file, then maybe there's no actual need to pay for following these pointers to somewhere else on the disk if you just stick the data in the file descriptor. So Linux actually does that for very, very tiny files. All of the data of the file is just sitting in the file descriptor, which is, as I said, also sitting somewhere on disk. So, disadvantages, as we make our files larger, random access is basically getting more expensive because we're potentially having to follow multiple pointers. Still going to be reasonable, but that is a downside. And again, we're still getting lots of seeks because their actual data on disk is not laid out contiguously. Right, so again, we still are essentially not as good as the really simple contiguous allocation approach for actually doing large sequential reads. Now, something the OS can actually do to help with that is sort of default to just laying things out in a sequential manner, right? Because if you have a disk that's mostly empty and you have lots of free space, your OS can basically just choose to lay things out by default contiguously. And if you run out of space and can't continue to do that, then you can actually go and start putting pieces of data elsewhere. But you can basically default to just laying things out contiguously and only start moving things, only start pointing all over the disk when you actually need to. Yeah.
Is there any way to specify a block size? I think that would also
The block size? Yeah, so actually when you create your file system, you can basically specify what you want the block size to be. Right, so that's again essentially the difference between the block size and the sector size. The sector is defined by the disk itself. That's the basic unit of I/O. But the block is actually a file system construct that can be, some multiple of the sector size, basically. So, as I mentioned, this is basically the approach that's used in all modern varieties of Unix. So it was introduced, a while ago in BSD Unix 4.3. Now, one other thing you actually could do for contiguous access is run a disk defragmenter, right? So I assume that's a term most of you have heard of. You can download a utility for your machine, a disk defragmenter, and when you run that, it basically is reorganizing how everything is laid out on your disk in order to get everything as sequential as possible, basically. Now, of course, if any of you have actually run a disk defragmenter, their running time is measured usually in minutes to hours rather than milliseconds or however long your computer is sort of running at. So a disk defragmenter is really, really expensive and not anything that your OS would sort of ever choose to do itself. So that is an option that is sometimes used. So last thing I want to talk a little bit about is managing free blocks. Right, so in all of this, whenever you want to allocate a new file or you want to allocate more space to a file, you obviously need to get, you need to find some free blocks of your disk to allocate. So this is basically called a free space list. Is basically the list that your OS maintains of all of the blocks that are available to allocate. And of course, you want to be able to allocate free space, quickly and efficiently. So one basic approach we can use is to use a bitmap. So I assume some of you are familiar with a bitmap, but basically it's just going to be one bit for every block of your file system, right? So, it's basically just going to be a string of zeros and ones, and this is basically just going to say each block of my file system, it's either used or it's not used, right? So this is going to be, this could be, block 0, and this is, block 1, so this is saying, block 0 is available. Blocks 1 and 2 are used, block 3 is available, so on and so forth. Right, and that can just be stored as a bunch of bits, which is very, very efficient. You're only having to store 1 bit per block. And then you can do things, the typical way it's done to actually find a new block in this approach is you can basically just take chunks of 32 of these bits. Right, 32 bits is an int. Right, and so your computer can basically just take 32 of those bits, compare it to 0, and that will basically tell you if all of the pages are in use or if there's at least one free page. And then once you find something that has at least one free page, you can just go into that 32-bit chunk and look for the bit that has 0. And once you find a bit that's 0, that basically tells you, here's a page that I can now allocate, and then you obviously just flip the bit. So now, one thing here is that we, again, are basically having to keep a copy of this bitmap on the disk. Now, typically you're going to be, again, modifying it in memory, but periodically you're going to have to write it out to the disk so that you're keeping track of what parts of your disk are free. But, this could potentially be a problem if you have a really large disk, right? So if you consider something like a 2 terabyte disk and 512 byte sectors, your bitmap becomes very, very large. And it gets to the point where you might be, using hundreds of megabytes just to store the actual bitmap. And, furthermore, that means that if your disk is very, very full, if most of these things are ones, then you're potentially having to go through a lot of the bitmap to actually find a 0 bit. So that might become very expensive to actually find new blocks. So, basically a different approach is something we mentioned earlier, which is essentially just keeping, a linked list of free blocks, where you're just keeping the one pointer to a free block somewhere, and then it keeps, pointers to, subsequent blocks in memory. So that type of approach is more typically used than the bitmap approach because, disks have gotten really big and are obviously getting even bigger. So that's pretty much it for talking about how data is stored on disk, right? So we again started with contiguous allocation, nice and simple, but have the same issue as in memory. We have external fragmentation, and so then we moved to using index allocation, and then using a multi-level index, we can have small data structures while still allowing for very large page sizes. So I think we'll stop there. So next class, we are actually going to start talking about how we actually read from a disk.